I'm very happy to be here to have also this opportunity to talk about our work on stochastic network calculus. And I'm particularly happy to do that here because I started working on this topic a little bit north of here in Djursholm at the Institute Mittag Leffler that 10 years ago had a one-semester program on queuing and teletraffic theory that provided a lot of useful and interesting input to me and enabled me to work on this topic. So, as I said, my talk is on this stochastic network calculus, which is a theory for performance evaluation of communication systems and computer networks. And in this talk, I will frequently make connections with system theory to motivate the models that we use in this network calculus. So I will start with defining a system model of a queuing system, and that particular system model has the property of being time variant. So we consider systems that may change over time, and viewing these time variant processes as random processes, we can then advance towards a stochastic formulation of networks using this network calculus. I want to show what the difficulties of this theory are, or what difficulties this theory encounters, what are the methods to solve these, and then I want to highlight some of the main applications, some of the main results that can be derived from this. And in the third part, I once again want to make a connection with system theory. So there is a transform, the Legendre Fenchel transform, which provides a number of useful insights and further applications of this theory. So in general, we are interested in packet data networks. So we have, as a simple example, number of routers interconnected by links. These links could be wired links, it could be wireless channels, and then there is a number of flows that use this network. These are packet data flows, so there are packets flowing through this network, and we have certain points in the network where packets are being multiplexed, flows are being multiplexed, or later on being demultiplexed again. And whenever flows are being multiplexed, we need to deal with the situation that several packets may come in that have to be forwarded to the same outgoing link, and then we need to have some buffering to bring these packets into a certain sequence. So that brings us to the abstraction of a network as such a queuing network where we have buffers at the typically routers outgoing interfaces. Packets are stored there and then forwarded. The service rate of these servers here is now the capacity of the outgoing link, and then packets traverse the network. The reason why one does this multiplexing of flows is basically resource efficiency. So we can achieve significant statistical multiplexing gains by using this type of packet switch networks. On the other hand, it has, of course, impacts on the quality. So we may have backlogs in these buffers, and that may, of course, result in delay. And that's basically what we are interested in analyzing. What are the multiplexing gains, what are the statistical gains, and what's the impact on the service quality. To this end, we need to have a system model of such a queuing system. So I will first now look at a single queue. And what we do is we model these by a service process S with two arguments, tor and t, and S defines the amount of service that is available in an interval from tor till t. These bivariate processes now allow a time variant formulation because this interval may differ from an interval of the same width a little later or a little earlier. So it's the width of the interval, that's t minus tor, that matters, and also the absolute position of this interval in time. So systems may change over time. The reason may be a wireless channel that is time varying by nature, or it may be cross traffic at systems which consume service and makes the service time varying. Now with this definition of a service process, we can proceed to investigate such a basic queue. We have arrivals A of t entering the buffer. This is cumulative number of bits over time. So we just count the number of bits that arrive at a system starting at time 0 up to time t. So these are generally non-decreasing functions. These arrivals are placed in a buffer. So due to the buffer, we have a lossless model right now. Data is being served by the server, and then departures d of t leave the system, and that's again cumulative number of bits that we count at the output of this queue. Generally, d of t is also non-decreasing, and d of t is always smaller equal than a of t. So data can only depart after it has arrived, obviously, And if d of t equals a of t, so everything that arrived has departed, then our system is empty. So that's what is the condition for having an empty system. Now with these definitions, there is a very fundamental queuing formulation of such a system, and it makes the additional assumption that the system is work conserving. That means the server is not supposed to idle if there is work to do. Whenever there is work in the buffer, the server has to use its service and forward data. So that's what work conserving means. And for such a system, we can relate the departures, d of t, to the arrivals, a of tau, and the service, s of tau and t. And the formulation here uses a minimum. So what this minimum does, it evaluates this expression for any tau, and then we take the minimum of all these values. So that's how the departures are computed from arrivals and service. I phrased this as an inequality here for basic work-conserving systems with time-varying capacity. That actually holds with equality, but in most cases we can do just with an inequality. So in the network calculus, a lower bound for the departures is usually sufficient, and that allows us to model more complex systems where we may not have exact solutions, but can only provide such a lower bound. To provide a bit of intuition what this expression does here, you could view the minimum as selecting the largest time tau at which the system is empty or was empty for the last time. So the minimum just picks the tau where the system was empty for the last time, meaning at time tau, a of tau equal d of tau, everything that arrived till tau departed till tau, and then the system is busy starting at time tau all the period long, meaning if it is busy all the time, then it consumes the entire amount of service. So if we replace here a of tau by d of tau, that's the departures up to time tau, and then we add just the amount of service that has been consumed in the interval from tau till t, and since the system was busy all the time and created departures, this then gives us the departures at time t. And I abbreviated this formulation here by an operator. This is known as a convolution operator. You may, to see this first, consider an integral instead of the minimum here, and a product instead of the sum. Then you have the convolution in classical algebra, as you probably all know. And by replacing the algebra, switching to an algebra which has only the operations minimum and addition, this min plus algebra, we have a convolution operator in min plus algebra here. To show a system that actually has this time variant behavior, want to consider an initially time invariant system that has a constant capacity C, and at this system we now schedule through traffic, that's the flow we are interested in, and there is cross traffic, meaning there's traffic by other users, which also consumes service. And such a system can in the network calculus be expressed by what is called a leftover service process. So the general approach here is we consider the capacity that is available overall, and from that we deduce the amount of cross traffic that consumes service, giving us a so-called leftover service process here. And what happens there is first we have a time invariant system with a constant capacity C, but due to the deduction of the time varying cross traffic, we end up with a time variant leftover service process. The important thing with this leftover service process is it again satisfies this min plus convolution. So we can now compute the departures of the through traffic from the arrivals and this leftover service process, meaning the system with cross traffic can be substituted by a system without cross traffic if we model this system as this leftover service process. So that's an important feature for analysis of networks. We can basically get rid of the cross traffic and put that into the leftover service process, and then only consider the through traffic that traverses a system with this leftover service process. And there are quite a number of works on scheduling in this framework of the network calculus. So right now there are stochastic leftover service models basically for all major schedulers available. So that includes FIFO, weighted fair scheduling, priority scheduling, earliest deadline first scheduling. So all of these are included in refined models of this leftover service approach. And there is an interesting connection also with wireless systems. So you could also view a wireless channel as having a constant capacity that is impaired by some impairment process, which could be fading, which could be interference. So there is some impairment which is being deduced from the capacity of the channel. And in that way, also wireless channels can, to some extent, be mapped to such leftover service models. Again, important thing here is that satisfies the min plus convolution formula. So it's this general operator that is being used to compute departures from arrivals. And the importance of having this convolution operator is that it has actually a catalog of nice properties. And I will only use one here, that is the associativity. So we can regroup the brackets here, but there are many more useful properties of this convolution operator. And a word of caution, this convolution operator, if we consider time variant systems, is not commutative. So for time invariant systems, it is commutative. Here it is not commutative if we consider time variant systems. Now for the associativity, that has a very important application in the analysis of tandem systems. So I now consider a first network consisting of two systems, S1 and S2. We have arrivals that traverse the first system. So we can compute the departures at this point as A convolve with S1. That's now the arrivals to the second system. So we convolve again with S2, and then we get the departures of this tandem of systems, and that basically extends to any number of systems in tandem. So this is the expression that we have, and just by application of associativity, we can regroup the terms, and what I do is I substitute S1 convolved with S2 by S. So at the end, I have this function S, that is S1 convolved with S2. This function S expresses the arrival-departure relation of this network of tandem systems, meaning what this implies is there is a single equivalent system, S, that behaves identically to this tandem of systems. So that's probably the most important result of the network calculus. It implies that anything which we can derive for a single system extends immediately to a tandem of systems. So any result that we have for a single system applies to a network of systems, because we can concatenate this network of systems into a single equivalent system. So that's the most important feature here of this convolution operator. There is another reason why these convolution form networks are preferable, that is the numerical precision of performance bounds that can be derived thereof, and this has been coined as pay bursts only once. I want to illustrate this using an example. If we have this tandem of systems, we could compute the delay, a delay bound for system S1, and we could compute a delay bound for system S2, and considering this end-to-end, we could just take the sum of the two delay bounds. If we do that, it can be shown that we actually account for the burstiness of the through traffic twice, and a tight delay bound, on the other hand, has to pay the burstiness of through traffic, this traffic, only once, and it has been shown that such tight performance bounds can be derived from these convolved networks. So also regarding the numerical precision of results, it is generally advantageous to have these convolution form networks. And once we have that, it's straightforward to compute for a given arrival process using the service characterization of the network, compute the corresponding departure process, and based on these, we can immediately define performance measures. So the delay of a first come, first serve system is the horizontal deviation here. So we could view this as the arrivals up to this time. Everything that has arrived up to here has departed until here, and that is basically the delay of the last unit of data that was transferred here. The same for the backlog. So at some time t, this is what arrived until time t, minus what has departed until time t. The difference is what is still in the system. And generally, these vertical deviations can be phrased more easily. So if I want to write it down as an equation, then formulating the backlog is much simpler. That's just b of t, the backlog at time t, is the arrivals minus the departures. For the delay, the formulation looks a bit more complicated. There's a bit more notation, but it can be done in the same way. But the backlog is more illustrative. That's why I will mostly use backlog in this talk. Now, what we do is we replace this convolution formula inserted here for d of t, and then due to the minus get a maximum expression here. So the backlog has this upper bound of the maximum of a minus s over any time interval from tau till t, and we need to evaluate this for all tau and take the maximum of this. So that's the way how to compute the backlog, given we know arrivals and departures of a system. Now, in a real network, we would not exactly know the trajectory of the arrivals and of the departures, but rather have some statistics of the arrivals and also of the service. So what we do is we now make the transition and view these as random processes. And with these random processes, we can then derive statistical guarantees which take this form. So what we are interested in is to find the probability that the backlog exceeds some threshold, small b, and that probability is what we name epsilon here. So we want an upper bound on the probability that the backlog at some time, or the stationary backlog, exceeds some threshold b. And we had this formulation of backlog on the previous slide. The difficulty now is that this backlog formula doesn't look at basically two random variables. It's not a and s, a random variable, but what this does, the maximum, it evaluates all tau. So it looks along the entire timeline, along the entire trajectory of arrivals and service, and evaluates these sample paths of a and s. And it cannot be easily solved by fixing this tau, so there is no a priori known tau that achieves the maximum, but this tau star that actually achieves this maximum can be shown to be a random variable, since it is depending on a and s. So there is one fundamental challenge to deal with these sample paths of arrivals and service that kind of recurs in the stochastic network calculus. And for this backlog expression, and also for other expressions, there are now basically two starting points where we can work on this. The first option would be to consider this residual process R equals A minus S. That is the usual approach that we take if we can assume statistical independence. So if the arrivals and the service are statistically independent, then it's the way to do to consider this residual process. On the other hand, if we don't have independence, then it's usually preferable to consider the arrivals and the service separately, find bounds for these, and then go on with these bounds. And both approaches use the same basic mathematical tool set. That's why I will only investigate one of these in more detail, and the second one is somewhat more illustrative. So I will focus on that, looking at arrivals and service separately, but the methods that I show can also be applied to the case where we look at this residual process R and take advantage of statistical independence. Now, to illustrate this a little bit, what these sample path bounds or envelopes mean, this shows number of possible sample paths of the arrivals, so that's data over time here. We have 4 different sample paths, so our arrivals are a random process which may take any of these trajectories that I depicted there. Now, what we want to have is some upper bound for these processes, and what deterministic network calculus does is it defines an upper bound that holds for any of these sample paths for any time. So we just consider the worst case of all the possible sample paths and find a bound for that. So that would be a deterministic envelope that can be used to analyze the worst case behavior of a network. Now, if we want to look at statistical performance guarantees, we can relax the condition on the envelope and, for example, define this dashed line here as an envelope. That's still an upper bound for our sample paths, but it now has a certain probability of overflow. So with a small probability of 1/4, there is at any time one of the sample paths that exceeds this dashed line. In this example, the probability is 1/4, so in numerical calculations, one would rather have a probability of 10 to the -6, so 1 out of a million of these realizations may exceed the envelope function, and that's now the definition of such a statistical envelope. The advantage here is we have this here characterizes basically the burstiness of the traffic, and what we get is a much smaller burstiness term here, means we need less resources, or we get smaller performance bounds, basically better performance bounds, with the price that these may fail with a certain small probability. Now this dashed envelope has still one problem, that is if we not consider a single point in time, but if we look along the entire timeline, we may actually figure out that it's not only one, but it's 2 of the 4 sample paths that exceeds this dashed envelope. So here it's the red one, there it's the blue one. So if we evaluate entire timeline here, then the envelope actually has an overflow probability of 2 out of 4, and only 2 of the sample paths are below the envelope over all times. And what we need to do here is we need to relax the envelope, so find an envelope that is a little bit larger. That would be this dashed dotted line, and that now provides a sample path guarantee in the sense that 3 out of 4 sample paths are always below the envelope, and there is only one sample path, the red one, that may exceed this envelope function. It does so twice, but that doesn't matter, so 1 out of 4 sample paths exceeds our envelope. The other 3 are below this, and that provides the desired sample path guarantee. Now to compute such envelope functions, there are a number of methods, and I just want to show an example. This is probably the first and most simple way of computing such an envelope function, and the general approach, or one general approach, is to start from the moment generating function of the traffic. So we have this expected value of an exponential of the traffic process here. There is a free parameter theta, and for this moment generating function, one can assume for a certain class of traffic that there is a linear envelope rate. So we assume there is an upper bound with a linear envelope rate available here. And with this characterization, we can use a statistical inequality, Chernov's theorem, and then compute an envelope function of this type. This now says the probability that our arrivals exceed this envelope rate by more than a burst term b is upper bounded by e to the power of minus theta b. So we have basically here an exponentially decaying overflow probability, and we have this guarantee that the arrivals in most cases will be below this envelope rate and this burstiness term b. That may, however, be exceeded with this small probability, and the larger b, the smaller this overflow probability. So that gives us this so-called exponentially bounded burstiness model. There is an exponential bound on this burstiness here. Again, this holds for any tau and any t, but it does not provide this guarantee that I spoke about on the previous slide. We want to have guarantees for entire trajectories for the entire timeline. And the guarantee that we actually want to have is this maximum. We want to make statement about the probability that along the entire timeline the arrivals may exceed the envelope rate by more than b. So we now look at all points in time, and the way to deal with this is, since we look at any point in time, we may have this overflow probability at any point in time. By use of the union bound, we could just take the sum of all these overflow probabilities for any point in time tau. Now you probably see what the problem here will be. Regardless how small the individual probabilities here are, if we take an infinite sum, we will just not derive a meaningful probability here. And the contribution is here to add a slack rate, so we relax this envelope function by a small slack rate delta. So this delta is added to our envelope rate, and in this way we get a overflow probability that decays exponentially with time, and that can easily be integrated or summed as a geometric sum, so that gives us this finite overflow probability here. So there is again the exponential decay in the burstiness, and there is some factor in front of this. So that is one method how to get these envelope functions for a general class of traffic with linear moment generating function bound, or for traffic of class EBB. And there is something else to observe here. We initially had bivariate functions to describe time variant systems. These are now characterized by an envelope function that is univariate, so here only the width of this interval matters. So by assumption of stationarity that we use here, we can transform the bivariate functions of the time variant system theory to univariate envelope functions. If we can make stronger assumptions, so if we would consider a process that is not only stationary but also has independent increments, like a Levy process, then there are tighter bounds available. There are better ways of computing these envelope functions. One approach that is recently used is to define a martingale and use Stoops martingale inequality. What that provides is basically the same type of envelope, now with an also the same exponentially decaying probability here, but with a refined prefactor, so that enables us to increase or improve the numerical accuracy. To illustrate that, just an example, this is the well-known MM1 queue, and what I'm showing is a delay bound that is exceeded with a certain small probability epsilon. So if you look at 10 to the minus 6, what this says is that a delay of 30 milliseconds is exceeded only with this probability 10 to the minus 6. And for these MM1 queues, we have closed form exact results, so that's what this blue line is. And for comparison, I included the bounds that we get from the network calculus. So this green line is what the Dupe martingale bound gives, so that may be approximately 32 milliseconds. And the red line, that's the Chernoff union bound, so that's about 40 milliseconds. So you see, we can improve the numerical accuracy of these bounds and can get very tight bounds for certain processes. The probably more important observation here is that the general qualitative behavior of the system is represented correctly by any of the bounds. So we generally have this exponential decay here, and also the rate of this decay is correct by any of the models. So also using Chernoff union bound, which gives slightly looser bounds, provides, however, the right qualitative behavior of the system. Now, what I looked at in the previous example is this class of Poisson processes, where we have all the nice exact solutions from queuing theory. With the network calculus, it is of course interesting to look at more general processes where we may not have exact solutions. And if we classify these processes coarsely, the next wider loop here is the class of Levy processes. That's where we can have very tight martingale bounds. Then we have Markov processes. These have this linear envelope rate that I spoke about earlier. That method that I've shown can even be extended to moment generating functions that have an affine bound. So there is an additional burstiness term that also is EBB. And then in the outer circle, what I marked here as dark gray, we even have more demanding processes where the moment generating function may exist, so we have finite moments. However, the traffic may not have any linearly bounded moment generating function. And one prominent example here is fractional Brownian motion. So that is a model that has been frequently used to model internet data traffic, as it is self-similar and long-range dependent. So these are properties that are frequently found in internet traffic traces, and this fractional Brownian motion has a moment generating function, so we have this characterization by a moment generating function. However, it has a linear rate and it has a variance here with a parameter t to the power of 2h. H is the Hurst parameter that basically specifies the amount of long-range dependence. If h is greater than 0.5, then our process is long-range dependent, and the difficulty here is now that this time parameter grows superlinearly in t, so we don't have any linear rate envelope for this class of MGF, and that makes deriving solutions envelopes for this process more difficult. So the problem here is we cannot directly apply this method that I've shown with a linear slack rate. We can, however, find some adapted slack parameter here that now has a time parameter which has this exponent 2 minus 2h, so that one is complementary to this one basically, and for h greater than 0.5 this time just progresses, or this time parameter has a less than linear influence. What that results basically in is that our overflow probabilities cannot decay exponentially fast, which makes integration or summation of this more difficult. I don't want to go into the specifics of the derivation, but rather show the much more interesting results that can be derived from this, since these have very important consequences for the dimensioning of networks. So what I'm showing here is a backlog bound, small b, and an overflow probability epsilon. And this is now the probability that the backlog exceeds this threshold, and you could view this as being the probability of buffer overflow. So we provision a certain amount of buffer, and this is the decaying probability that the buffer overflows. And the blue lines here, this is Markov on-off traffic, belongs to the friendly class of EBB traffic. That generally shows this exponential decay. So this is on log scale, so we have straight lines going down here. There is a burstiness parameter t. The slope of the decay depends on this t, but generally we have this exponentially fast decay. And the consequence here is that providing a little bit of buffer space just reduces the buffer overflow probability tremendously. So whenever we find that the buffer may overflow too frequently, we just need to add a little bit of buffer, and then the overflow probability just virtually vanishes. On the right side, on the other hand, we have the curves that apply for the fractional Brownian motion. And then we have the Hurst parameter. So here, with increasing Hurst parameter, the slope becomes significantly slower. So the probability that a buffer overflows decays much slower with the buffer size. What that means is, even if we provision very large buffers, there will always be some residual probability that the buffer overflows, and even worse, it implies that these large buffers may actually fill and cause very large delays with a certain probability. So for FBM traffic, we from this graph have the conclusion that buffering is by far not effective. And formally, this has a Weibull type decay, so it's log epsilon proportional to the decay is proportional to b to the power of 2 minus 2h. So again, there is the Hurst parameter, and if h becomes large, approaches 1, then you see that the buffer just has only marginal influence. So this asymptote has been known previously for b to infinity. With the network calculus, we can basically confirm that result also in a non-asymptotic regime. So we have that now as a strict upper bound. Now, speaking about network calculus, what is of course more interesting is not a single flow at a single constant rate link, but we want to have networks where there are several flows in the network, and to this end we also need to consider the time variant and random service. So there we can basically use the same steps. We consider sample paths of the service, compute now again envelope functions but lower envelopes, so we have a lower bound on the amount of service that is available, and these service envelopes I denote as epsilon. They may be directly substituted into this convolution formula, and The concept is also then known as a statistical service curve. So we now get a statistical guarantee from this definition of service envelope of this type that the departures will be greater than A convolved with S with a high probability, and only with this small epsilon, the departures may fall below this service guarantee that we can provide here. So that's a way to characterize the service by what is called a statistical service curve. And then we can proceed to networks. Said earlier, we want to have these convolution form networks, so we want to take the convolution from one node to the next and then combine all of this. And that actually turned out to be quite a challenge. So that was a long-standing challenge because this definition that I've just shown here cannot provide this convolution end-to-end through a network. The reason is we have this minimum here that evaluates all tau, so it looks at an entire sample path of the arrivals, but the service guarantee only gives us a pointwise guarantee for the departures. So this is valid for any t, but we need to fix t. Now the departures of the first system will be the arrivals to the second system, and the second system will, again, for the arrivals, then need a sample path guarantee. So that's kind of the fundamental problem here. The out guarantee of this service curve formulation is not for sample paths. However, at the input of the next system, we would need a sample path guarantee. And there has been an attempt to define a stronger type of service curve. So one could try to solve this by defining a stronger guarantee. So the difference here is we now want to know the probability that the departures are greater than this expression for all t. So just by adding this for all t, here we would formulate a sample path guarantee. We want to have a guarantee that's not only valid for a single, any arbitrary but single t, but it shall be valid for all t. And if we define that, we can immediately do the convolution. So this definition of service curve can immediately be convolved. It has, however, been shown that this definition actually is more or less an empty set. So for ergodic processes, it has been shown that this definition here is essentially deterministic. So this epsilon prime is either 0 or 1. One cannot have meaningful probabilities here. So the definition of the stronger service curve would solve the problem. However, the class of processes that falls into this is essentially void. So that did not resolve the problem. Now, today there are, however, two basic methods available that achieve these convolution forms without requiring further assumptions. And one is the statistical service curve by Ciucu, Liebeherr, and Burchard. That now again introduces a slack parameter delta, and that is introduced in a non-obvious and non-trivial way. So there is a very sophisticated way of adding this slack term delta so that the set of processes is not empty, but it achieves this convolution. And from these convolution form networks, performance bounds have been derived that could improve previous results from On to the power of 3 to On log n. So this is now, if we consider a system or a network of n systems in tandem, and we ask how do the performance bounds, delay bounds grow with each additional system. And this n log n basically means they grow superlinearly. So adding another system will give it a more than linear increase of the delay. So delays grow as n log n. That is a quite surprising result and motivated the search not only for an upper but also a lower bound, which was also found by the same authors. So it was shown that both upper and lower bound are in n log n, so that's asymptotically tied, that result. So performance bounds for n systems, statistical performance bounds, grow as n log n. The second method operates directly on service processes. So there is a second method that also achieves this convolution. And the approach here is now to work directly on the service processes, compute a service process for the entire network by a convolution of the individual service processes, and then consider the moment generating function of this there is a bound for this moment generating function. So what we can do is we can convolve the moment generating functions of the service of each system to get a statistical description of the service of the end-to-end network. And this approach uses independence, so that's a difference to the assumptions of the first approach. Here, independence of the individual service processes is required, and if we have this independence, we can now find performance bounds that grow linearly in the number of systems. So finding here is if the systems are statistically independent, then adding another node will just give us a linear increase of the delay. Same result has been recovered by Hussein Al-Zubaydi recently for wireless networks. So there is an SNR calculus which can do this for fading channels. So if we have a tandem of n fading channels in series, then the delays for such a network grow linearly in n if these fading channels are statistically independent. Now, if you would think of having a common interferer, so all these channels are interfered by one interferer so that the service would not be independent, then we would not have this O of n, but the n log n growth of delays. Taking this further to networks with fractional Brownian motion, we can also consider a through flow here that traverses n systems, and at each of these systems we have cross traffic that has this type of fractional Brownian motion. So this is now a long range dependent cross traffic, and what we compute is a delay bound for this through flow that traverses all of these n systems. And again, there are some scaling results available. So now we find that the delays grow as n log n, and this logarithm has an additional power here. So there is a polylogarithmic growth that depends on h. Again, if h becomes large, goes to 1, then the exponent of this log term becomes very large. So if cross traffic is highly long range dependent, has a large h, then the price for each additional node that is traversed in terms of delay becomes higher and higher. For h equals 0.5, that is the special case of Brownian motion, the Hurst parameter is 0.5, and then the result recovers the previously known n log n result that applies to the EBB class. Graphically, I'm showing here in this graph now delay bounds for n tandem systems, and to focus on this logarithmic part, I divided the delay bound by n. So this is just the log that remains here. And again, EBB, that's the friendly traffic. So we have this logarithmic growth. The growth is somewhat larger if we have a larger burstiness, but it's always a single logarithm there. On the other hand, for fractional Brownian motion, with increasing Hurst parameter, our curves just tilt, and the price for each additional node grows basically polylogarithmically. So that's some explicit results that this theory of the network calculus provides for the behavior of delay bounds over entire networks. And in the last third part of this presentation, I want to once again go back to the relations of the network calculus and system theory and motivate the existence of a transform in this network calculus. That is motivated by an observation that there are certain eigenfunctions. So I go back to these convolution operators. We have the arrivals convolved with the service curve here. And if the arrivals are affine functions, then one can actually see that these affine functions are eigenfunctions. So convolving an affine function with S just reproduces the same function and an additive eigenvalue here. Now I could have put the minus into the eigenvalue, so that's an additive eigenvalue essentially. And this eigenvalue has the interesting property that it is actually the Legendre-Fenchel transform of the service process. So what that means is we have a transform that is motivated as the eigenvalue of these eigenfunctions of min plus convolution. And this transform is also well known in convex optimization, also has a catalog of nice properties. One important property here is that it is its own inverse as long as we are talking about convex functions. So applying this Legendre transform twice just recovers the same function if it is convex. So what that means is we can take, by Legendre transform, the functions into a different domain, and another transform brings the function back into our time domain that we have been operating in previously. And based on all these further properties that this transform has, one can argue that it takes basically the role of the Fourier transform in this min-plus algebra of the network calculus. And moreover, it has a very nice interpretation. So the Legendre transform of this service curve basically has the interpretation of being a delay bound, statistical delay bound for constant rate traffic. So if we take the Legendre transform divided by C, the data rate of constant rate traffic, then it gives us a delay bound for the system. So what that essentially means is we take, by Legendre transform, functions where we had data expressed as a function of time into a domain where we can phrase delay as a function of the rate. So we get the delay of the system if we use it with constant rate arrivals of rate C. And the converse can also be done for the arrivals. Now I consider arbitrary arrivals, A with an envelope function, take the concave Legendre transform of that, and this is now a delay bound that applies for these arrivals if we would transmit them over a system with constant capacity. So also that has this interpretation of being a delay. Now for arbitrary arrivals, it's the delay at a system with constant capacity. And based on this property, we can actually motivate a model that characterizes sources and systems by capacity delay boundaries. So we take the Legendre transform of the service process and thereby obtain a boundary trade-off of capacity and delay. And for this example here, I borrowed a model of a Rayleigh fading channel from Hussein Al-Zubaydi and co-authors, and transformed this into the Legendre domain. And what this now basically tells us is that Rayleigh fading channel has a certain SNR, and depending on that SNR, it can provide a certain average transmission capacity. That would be the result that we get from information theory. So there is a certain limit, certain transmission capacity, which we cannot exceed. Now this capacity delay boundary adds to this notion of capacity a price in terms of delay that we need to pay if we utilize a certain amount of the capacity of the channel. So if we pick the case of 15 dB here, the channel would have an average capacity of up to almost 18 megabit per second. However, if we use it at a very high rate, if we transmit data at a very high rate over this channel, if we approach this capacity limit, then we have to pay a very large price in terms of delay. On the other hand, this curve tells us if we have a certain delay budget, if we want to have an upper delay bound, then we may use this channel only up to a certain capacity, up to a certain data rate. So we can transmit a constant data rate source over this channel and tell from its Legendre transform what's the delay that we will incur. Similar curves we can also generate for sources. These now look exactly, have the opposite shape. What this tells us here is what's the capacity that require to transmit a certain traffic source, and now the average data rate of the traffic source is this asymptote here on the left, and if we provision more capacity, then we will find smaller delays when transmitting this data source. And the example that I picked here is a MPEG video traffic trace, which we encoded using different quantization parameters. So this quantizer here basically determines the quality and the data rate of this video. Smaller quantizer means higher quality video and higher data rate, basically. And again, this Legendre transform gives us the information. If we transmit this over a constant rate channel, then we would have to pay a certain amount of delay as the price, basically. So what we have is these two models for sources, for systems, and owing to the properties of this Legendre transform, there are a number of results from convex optimization which can easily show that these two functions are additive. If we now want to consider transmitting the video source over the Rayleigh fading channel, convex optimization results tell us we can just add their capacity delay boundaries. So I will just show that for one example. So I pick an SNR and a quantizer. Quantizer is 22, SNR is 12. I now want to transmit this video with quantizer 22 over a Rayleigh fading channel with 12 dB and find out what's the delay bound that we need to consider. And the result here is we take the sum of the green and the blue curve, getting this black dash dotted curve, and the mathematical result basically says we can optimize over this parameter C. So what we basically find here is the minimum that tells us we can transmit this video source over that channel with a delay bound of 100 milliseconds. So that's the result which we get for the composition of sources and systems. Quite general result. In the next graph, I just phrased this cross-layer relation between parameters of the source and parameters of the channel as achievable regions. So we now have the quantizer here on one axis, the SNR on the other axis, and a target delay bound of 300 down to 100 milliseconds. And any point in the upper right corner, so upper right of this blue curve, any of these points essentially achieves this delay bound of 100 milliseconds. So this tells us what combinations of channel SNR and quantizer of the video can work together to achieve this delay bound that would enable adaptive video applications. So we can now make this cross-layer connection. Given we know the SNR of the channel, we can adapt the video quality such that the data rate matches the capacity of the channel, and a certain overall delay, target delay, can be achieved. And we could also do the converse. We can adapt the capacity of the wireless channel by adding additional resource blocks. So that is something we did even in an online algorithm. So we can adapt wireless resources according to the requirements of a video transmission. We can, in an online algorithm based on this network calculus framework, even take the actual send buffer filling into account, and on some epoch length then adapt resources such that the send buffer does not overflow, or such that target delays for the transmission are being secured. With this, I want to conclude my presentation. So I try to give a bit of an introduction into the framework of the stochastic network calculus. The difficulty when working with this is the necessity for sample path analysis. I showed that there is basically several techniques available today how to deal with this. So most is based on moment generating functions and chain of union bounds. There are also martingale bounds for certain special cases. So it always depends on how strong assumptions on independence one can make, what method to use. But we basically have solutions for all relevant cases with or without statistical independence. And I think there is a quite large application potential of this theory. So we have a large variety of different arrival and service processes that can be included into this model. There are even hard arrival processes with quite unfriendly statistical properties. For the systems, we even have network service processes. So I just showed the example of the tail decay, which shows that buffering is not effective for long-range dependent traffic. We have these fundamental scaling results for networks, and owing to this general concept of service processes, we can include also wireless systems which also may have difficult service processes there. Using these connections with Legendre transforms and convex optimization, we have, as a model of wireless systems and sources, these capacity delay boundaries, so we can add a notion of delay to capacity results. And these Legendre transforms enable a further application which I did not speak about. They enable applications in measurement-based estimation of systems or even system identification, so we can can take measurements of the arrivals and the departures of a system and then infer what's the service of a system which we do not know. So that's kind of a black box approach. The system service is unknown, and from observations of arrivals and departures, we can, via certain properties of Legendre transforms, infer what's inside the system. If you're interested in any of this, there's a list of references, and we quite recently published a tutorial on this, so if you want to get some easy access to some of the basic results that the network calculus provides, that tutorial hopefully provides this to you.